There's another way to look at this system. It was x1 plus 2y equals 4, 4x1 plus 8y equals 24. For the notation we're going to use here, I changed y to x2. So instead of using y, I'm using x2. The equation translates to the matrix equation ax equals b. X being a vector, b being a vector, A being a 2 by 2 matrix in this case. So the A matrix would be the matrix you see here, the 1, 2, 4, 8. The X vector is the column vector x1, x2. The B vector, the column vector 4, 24. So this matrix equation for these matrices and column vectors is equivalent to this. Because, why? Well, let's just write out what AX equals B means for this A, this X, and this B. Now there's A, there's X, there's B. Multiply through by this matrix and we get x1 plus 2x, 2x2 for the first row. And first row times the column gives us this. Second row times the column gives us 4x1 plus 8x2, still equal to 424. The two matrices are equal if and only if the corresponding entries are equal. So this entry has to equal this entry. Well, this entry is the left-hand side of this matrix. This entry is the right-hand side of this, not matrix, but equation. Okay, so that the first row equal to the first row gives us this equation, which is just this equation. Second row, second number in the column equals second number in the column gives us this equation, which is identical to this equation. So this matrix equation is identical to the original system of equations. Solution to the matrix equation AX vector equals B vector is, well, A inverse times the left-hand side. A inverse times A gives you the identity. Identity times the X vector just gives you the X vector. So we've isolated the X vector on the left side just by multiplying by the inverse matrix. And then we multiply by the inverse matrix on the left of B, just as we did here on the left of the AX. And that's what we've got. So the X vector is the inverse matrix times the B vector. There's only one catch. Okay? A inverse must exist. Doesn't necessarily exist. Ain't always so is what I said here. Okay? A inverse exists, and it should be exists, if and only if the A matrix, that's the A vector, the matrix A inverse exists if and only if the A matrix reduces to the identity matrix by row operations. Okay, because of the fact that you can augment the A matrix with the identity matrix, reduce the A matrix, doing the same row operations for the entire row, including the row of what starts out as the identity matrix. And by the time this matrix reduces down to the identity on this side, this matrix will have been built up to the inverse. Okay? Only catch is you can't always reduce this matrix to the identity. If we try in this case, we're going to have to multiply the first by -4 and add to the second to get rid of the 4 here. And that's also going to get rid of the 8. We're going to have 2 zeros here. And we're not going to get to the identity because there's nothing you can do to get out of the fact that you're going to reduce this thing and have 2 zeros here. You're not going to get a 1 in the second row. Okay, so we ain't going to get the identity, so there's no solution. Okay, well, we make a few statements now. A matrix is invertible is equivalent to saying the system has a unique solution. Okay, because if the matrix is invertible, then you do get a solution, a unique solution for X. The inverse matrix times B just gives you one column vector, and its components have to be the same as the components of the X vector. So there's just one solution. System has a unique solution. I just said that. The determinant is non-zero. Now, if you don't know about determinants, kind of put that off a little bit, but that's equivalent. If the determinant isn't 0, you can reduce the matrix to the identity. If the determinant is 0, you can't reduce the matrix to the identity. Okay, so, and another one equivalent statement is matrix can be reduced to the identity. And another one is that the matrix is non-singular. Now that's just terminology. It says well, the determinant's non-zero, or it says the matrix can be reduced to the identity, or it says the system corresponding to the matrix has a unique solution. Okay, now you could raise an objection here. What about the system here? Now that's a system we dealt with here that reduced down to this, to an equation. You do have solutions, but the left-hand side is exactly the same as it was here. And the left-hand side is what gives you the A matrix, so the A matrix for this system is going to be the same as the A matrix for this system, but you can't invert that A matrix, but we still have solutions. We have infinitely many. We have a wealth of solutions. What's this tell us? Well, the key word up here is unique. System has a unique solution, just one solution. This system has infinitely many solutions. So if the matrix is non-singular, determinant's if the matrix is singular, determinant is zero. Matrix can't be reduced to the identity. It's perfectly possible you end up with something like this, and the system is reducible. And what it comes down to is whether you have a zero here or whether you don't have a zero here. Because if you don't have a zero here, you got 0 equals 0. If you do have a 0 equals 8 in this case, 0 equals something that's not 0, not true. Or down here you have 0 equals 0, and that is clearly true and doesn't contradict anything. Okay? So, and what I said here is, this is a good point if you ask this question. But the solution's not unique. There are infinitely many solutions. That doesn't contradict anything we said up here.